All right, we've got Codeforces Round 888 to Div 3 coming up in 10 seconds. Yeah, let's do it today. Actually roped in Scott Wu and Stephen K. Plus into participating too. All right, let's go. Always, here we go. That's a long description. These are very long descriptions. Okay. So 14 and 5. Okay, I see. And NM. Obviously P instead of H again, can't use the same variable. Diff mod, what is it, K equals 0 and diff K. I got tricked with using the small variables. No? Oh. Wow, that's tricky. Okay. Because, yes. Oh, not a good start. Very slow. Oh, Kanati's here. Alright. Those are some long statements. Both even or both odd? Oh my god, okay. This is so much easier to understand. So like A before sort I equals B indices I. How long does it take to know? Oh my god. Okay, I need to rearrange this a bit. Great. Oh, that is slow. Right. Ends at tile index n, p is divisible by k. Why are these statements so long? End of the tile index n, p is divisible by k. Okay. I see. Okay, so you never do any middle stuff. You should just... Yeah, if you see that front... And then... Okay, great. Okay, so... K occurrences of the first number and then K occurrences of the second number, and then see if you have any space. I mean, okay, maybe an easy way to do this is like, just be lazy. Okay, then we've just seen A less B. I think that's what we want. Yeah. Okay. Let's go very slow. So slow. So slow. Okay. Match rotation. Okay. Okay, so we have to split that. Okay, so there's a couple possibilities. We just take a diffs. Okay. for sure no. If they're all unique. So they're at least one, right? We know they're at least one. Well, we don't really need this, but I can just add it. Okay, and then if we have what? Oh, this is not actually. All right, so missing. What? The third one is printed yes. What is going on? It's so wrong. Oh, this didn't turn. Oops. Okay, that's what it is. Oh my god. Doing terrible. There's a lot of cases. I don't know if I did everything right. Why do we need so many? Okay, we'll just move on. Okay, so These descriptions are so long, every single one of them. The number of potions she already has. Costs. Which ones she has an unlimited supply of already. Type I. Distinct. Okay, well this is just the shortest path probably, right? It's kind of like a Dijkstra. Yeah, okay. Yeah, so we're basically doing... Right, okay. Did I forget K? I forgot K. Okay, I see. So then... Oh, that's not... No. Otherwise... Yeah, some is called CE. It's fine. It's fine. Okay. You have a party queue of events. CII, and then we have... We also want it in place. Mixed cost I. Oh, we need to know how much we dropped it by? How much did we drop it by? This one's won't work. How much do we drop it by? Because then we need to know. I can do something lazy. Okay, fine. I think this is what we want. Oh, this needs to be. Is this E? Okay, looking good. Oh, I guess F is easier than E. Non-negative interest less than 2K. Okay. Let's name any March number. X. Pair of numbers. AI XOR X and AJ XOR X. Oh, okay. So you can pick two of them. You just want them to have the most in common starting from the peaks. But don't you just put them in a try? You just put them in a try and just keep going. Go anywhere as long as there are at least two. In fact, you can sort them and they should be consecutive. I'll print the IJ. Okay, that's fine. But this is really easy. Yeah, this is easier than E for sure. 2 to the 2 to the 30. Okay. At least 2, right? Okay, and then well, it doesn't matter, right? You just this is not going to match, so we can just submit, I guess. Seems good enough. This is much easier than E. Yeah. Alright, G. Flat in the mountains. There's a road between the mountains. I and J. 3 minutes? What? Okay. I and J. Move from I to J. That's one. HJ minus HI. Be restored. Oh, what just okay, it's only can you get to each one, right? Because if you get there, you know what the energy is. And yeah. Are these bidirectional? It doesn't matter. Oh, there's quarries. Ooh, okay. Okay, there we go. So what's the min tallest thing? Okay, so like it's like yeah, we add mountains in increasing order of H, and we see how it really something gets connected. How do we? I don't think we do this in 3 minutes. Yeah, you want to minimize the tallest mountain you have to go to in between to get to. Yeah, okay, so yeah, you just do that and you want in the first moment these are connected. It's like the union find tree, I guess, in a weird way. Oh, I see. Can I do that? So I just build this tree, and then I'm querying the LCA. These are the edges in order. How do I use this? Oh, this says test cases. We can do these queries online at this point. Yeah, that's pretty sick. Okay, so let's not do that yet. Let's. I see. Oh, edges. Oh, I need to order the edges. Right. I don't know how you do this in 3 minutes. That's crazy. Oh, the H's can be the same. That's annoying because I don't want to do it twice. That's fine. Okay. So if make pair HX X so greater. And then we'll add it. And then semicolon. Oh, we just need to know, like, oh, they're just the edges in order. Yeah. Ooh. Okay. Alright, so now we want to know what is the AV, right? And then right, so we're going to take that. Basically, E is at least the highest minus HA. It's yes or it's no. Oh. Is it connected? Right, it doesn't have to be. Just continue. Okay. Oh, is this the problem? It's gonna build at 0, isn't it? No, that's correct. It's interesting. Why is that? Oh. That's really silly. That's so silly. Okay. Why is this not working? 0, 6. Oh, it's not giving me the right route, is it? Oh, I see. Yeah, it's not building the right way. I see. This is gonna work now. Oh, that was bad. Okay, cool. All right, be back in a bit to discuss the problems. All right, so contest is almost done. We're sitting in the top 5, and we can go over these problems. Actually, I was thinking I could clean up my code while I'm at it. Nice thing about Div 3 is you can actually just submit when you have cleaned up code. But all right, let's go through these. So, very long problem statements. I won't explain the whole problem statement, but we'll just go through the ideas for these. So, start with problem A. Problem A, you're given Vlad's height. You want to know, out of the list of people, who can Vlad stand and match heights on the escalator with? Basically, it comes down to a pretty simple condition. You just take their absolute difference in height. It needs to be a multiple of k, and then because there are n steps on the escalator, and each step has a difference of k, then we can get anything from k to n minus 1 times k. And so, sorry, m minus 1. So what we need is diff needs to be a multiple of k, and diff divided by k needs to be less than m. So it needs to be m minus 1, 1 through m minus 1. And notably, it cannot be 0. This is actually something that tripped me up on the sample. And once those are all true, then you have a match with the person. So we just add that all up, and that's our answer. That's problem A. Problem B. Right, so you can do a swap of any two elements, AI and AJ, as long as they're both even or both odd. You want to know if you can sort the entire array. So basically what this means is you can sort the even elements of the array in place and the odd elements of the array in place. Because if you have swaps, you can do a full sort. So we just need to implement that. The way I did that is not the best, so we can improve this. This is actually pretty easy to prove. So we just get rid of all this. Let's just find the indices and the values. And now we're just going to sort the values. And then, yeah, we're going to go through the... that's much better. So basically, for each value mod 2, we go through, we find the indices of where AI is that mod 2, and we take those values, sort those values, and then just put them back in the array. This is much better code than what I had in the contest. So we'll just submit that. Why not? Cool. That's problem B. Problem C. Yeah, this was a little hard to understand, but once you get it, it's not too difficult of a problem. Basically, you need to start at 1, you need to end at n. You need to end up on groups whose colors are all equal in each group, and the group has to have length k. You want to know if you can do that and go from 1 to n, and you can jump any amount. So basically, you know, you can see here we need to make a group with 1, so we do 1, 1, 1, and k is 3. So once we have 3, we're good. And here we have to end on a 4, so we need to make a group with color 4, so we can just use 4, 4, and 4. Yeah, so the idea here, there's basically two cases. If the first element equals the last element, then all you need is, there needs to be at least k occurrences of that color. If so, you're good. If not, there's no way to do it. Otherwise, you have this case where these are different. And this is just a greeting. You just find as many, if let's say this is 1, you find as many 1s as you can until you get to k of them. This is 4, you find as many 4s as you can until you get to k of them. And then as long as you find that many and this prefix and this suffix don't overlap, then you're good. That's basically it. So here we're just checking, are there enough of each value? We find the index of the last front value we need and the index of the first back value we need. Make sure they're in order, and if so, we're good. Yeah, so let's see. Problem D. Right, so we have the prefix sums of a permutation. Supposedly, we want to know if it works out, but we lost one of the prefix sums. So this problem, there's basically a handful of cases we need to cover. So what I actually did is I just took the differences of all these prefix sums. These differences should form the permutation. The only thing is that we need to either add one more value to these differences, or we need to split one of the differences into two differences that add up to the total, or that add up to the original number. This logic can be cleaned up a bit. It's going to be a bit shorter. So what we need, we actually don't need this because they gave that guarantee in the problem. We see which values from 1 to n we've seen. We see what's missing. I think we can simplify this a little bit. But basically the main logic is we find kind of the special number if there is one. Special number is either a number bigger than n. We know that number needs to be split up. If it's a number bigger than n, we have to have a missing size of 2, and then they have to add up to this special number. Otherwise, we find if there's a repeat number. If there's a repeat number, this number is kind of the special number as well. If there's no repeats, we just have n minus 1 of the numbers, 1 through n. We can just add one more number and we're good. If there's more than one repeat, then we have a problem. Or if there is one repeat, but the missing size is not 2, then we have a problem. Although I don't think that's possible, actually. Because if the repeat is 1, yeah, we don't need this. And then, yeah, same logic as before. The two missing values need to add up to the special number. So we could probably combine this logic somewhere. Anyway, this is probably fine. So this is a little bit shorter. Anyway, that's problem D. We'll keep going. Problem E. Okay, so this problem, we could definitely improve the code, I think. So, but basically, what I did is kind of like Dijkstra. You just solve everything in order of cost. When we have unlimited potions, that thing costs 0. Otherwise, we take the mix that we need to make it, and make the list and so on, and then we use our priority queue for Dijkstra. We add our options. This is one of our options, this is another option. And then when we kind of lock in an option, lock in a cost for something, we go through all the mixed lists in and then decrease the cost for that version. So this is kind of the Dijkstra idea. So let's save this. Let's see if we can do a different idea. What I want to do is topological sort. So yeah, so basically we have this graph, right? And mix this. Okay. So this will give us a sorted version of which things depend on which things. And we actually want to go in reverse order. Maybe we can just reverse this, and then we just solve them. So we have to skip if it's empty, because that means there's no way to do it. Otherwise, and I think that's good. So we don't need this value anymore. And the reason this works is because there's just a very simple dependency order on which mixes depend on which other potions, and so we just need to follow that order when we're trying to solve this. So this is actually a nice, it's a linear solution instead of the, you know, E log V type of Dijkstra that we had earlier. Cool, so that's E. So problem F. Yeah, so problem F, we're trying to maximize this value, AI XOR X and AJ XOR X. So if we think about, if we have an AI and an AJ, we want to maximize value by picking X. Well, basically for any bit where AI and AJ are the same, we can pick the value of X to flip that bit to a 1. And if AI and AJ are different in that bit, then there's nothing we can do. We're going to end up with a 0 after the AND. So we just want to maximize the it's kind of like the sum of the bits that are the same in AI AJ. And so another way to put it is we actually want the min XOR of AI and AJ for any I and J. So that's what we're looking for now, min or XOR of any pair. And it turns out if you want the min XOR of a pair, what you can do is you can just sort the array and then check the adjacent values. Because the idea is basically if you want min XOR, the greedy idea is you want the prefix from highest bit to lowest bit to be the same for as long as possible. So if you have two numbers, you know, like this, from high to low, then these bits are all the same, which means their XOR is going to look like this, and then finally you have a 1 here. And so, you know, the longer the string of zeros you can start with, the smaller your XOR. And you can just check adjacent values in the sorted list. And the reason is, given that you have this prefix being the same, and then you have this 1 bit here, you still need to minimize the bits afterward. But the thing is, if there were something else with, you know, hypothetically, if we had another number that had a 1 here that matched all of these bits, but had a better value afterward, we could use this number and that number, right, instead. So the idea is, you know, this number XOR this number is smaller because you get this value, but it actually would be better to XOR these two numbers instead because you get a longer prefix of zeros. So the idea is, given a certain longest prefix, you can only have one number for each bit, for the 0 afterward and for the 1 afterward. So that's why this adjacent strategy works. And yeah, so we just try those options. Once we have that, we know what A and B are, and then to get X, all we have to do is make sure that we flip all of the bits where they're both 0. The way I do that is I just take the kind of the bit inverse. I just flip all the bits of A, essentially. And then that's the answer. Cool, that's problem F. And finally, problem G. So problem G, so if we think about this condition, moving from I to J costs Hj minus Hi units. What that actually means is when we add up these differences, we can tell how many units of energy we spent to get to our current point. The only thing we need to know is where we started and where we are currently. We don't need to know the intermediate path. And so what's nice about that is then, basically if you go from mountain A to mountain B, then the maximum units of energy you've spent at any point, all you care about is what is the tallest mountain in between on your path from mountain A to mountain B, including A and B. And then that tallest mountain minus mountain A's height, that is the amount of energy you spent at your worst point. So we just need to know what is the kind of minimum tallest mountain that we can use to get from mountain A to mountain B. And so we're given this graph and all that. So there's a lot of ways you can do this. You can do this offline. You can sort the quarries by your highest mountain threshold. That would be HA plus E. That is the highest mountain you can use on your way from A to B. And then you can do this offline. You use union find. You can do this online. You can build the MST of the given graph, where the edge weight is the max of the two heights of the two mountains. And then you can query path maxes on this MST. And then a third way, this is what I did, is you can build the union find tree, which is an idea where you implement union find on these edges. You sort these edges by their max height between the two nodes. You unite them, build the union find tree on this, and then all you need to do is, when you get a query, you just need to query the LCA of A and B in this union find tree. And then we check if that edge's max height is within our range. So that's what I did. This is all like pre-written code. But yeah, you sort them, build the edges in order, make sure they're in order of the heights, build those trees, build the LCA data structure. A tricky thing here, I had to do some adjustments here because I actually had a problem where I didn't route the union find trees correctly. So I would query like, what is the LCA of 0 and 1? And I want to know the node in the union find tree with, you know, a big index where they finally got joined, but instead it gave me 0 as the LCA. So I had to fix that. But yeah, once you do that, it ends up being pretty simple. If A is B, it's just a yes. Otherwise you take the LCA. LCA less than 0 means they're not connected, so it's a no. Otherwise, yeah, the ancestor must be at least n and less than v. So this is what I mean, a big index. You take the edge that represents that, take the max of the heights, which is the value of the edge, and then you can just solve your query in O of 1. Yeah, so that's G. A lot of different approaches here. Maybe we should, oh, I realized I should probably, yeah, I had to like patch this together real quick, but I think a better approach is probably, instead of one root here, I think this should probably take roots and default to nothing. I think this is better. And so then what I can just do here is okay. Oh, I don't know if we can submit now. Hopefully we can. I guess we're in practice mode, yeah, so we're good. Okay, cool, looks good. Yep, accepted. Cool, and that is it. Yeah, we have the hacking phase, but otherwise, contest is done. So anyway, thanks for tuning in. Feel free to subscribe if you want to see future videos, but otherwise, I'll see you in the next one.